Hey guys, this is James and welcome to my short presentation on the Mandelbrot set. So first off, we're going to have to do a quick complex numbers crash course to make sure we're all on the same page. So as we know, we have a number line with 0 in the center, positive numbers on the right, negative on the left, and all of our decimals and irrational numbers can be found on this line. However, I, which is the square root of -1, where I squared is -1, cannot be found here. We have to add an imaginary axis to find it, which turns the number line into a complex plane. So there's I, and of course we have -I, fractional I, any real number can be multiplied by I, and you can find that on this imaginary line. So a complex number is any point on this plane, for example the yellow one, which can be represented as a plus bi, where a is the real component and b is the imaginary component. And this has the property where the distance between the origin and this point is its magnitude. And we're going to be looking at that a bit in just a minute. So what is the Mandelbrot set? To answer that question, we're going to have to associate a complex number c with this function in the yellow box, such that the input is the complex number z and the output is z squared plus c. And what we're interested in is the behavior of 0 under iteration of this function. What that means is we plug in 0 and we get the result and plug that in and repeat this process and see what happens. And we find that there are two possibilities. Either it blows up, which means it gets arbitrarily large. I have an example here where c equals 1, it becomes 2, then 5, then 26, and so on. Or it could stay small. In fact, it would always be less than 2. And I have an example here of c equals -1, and you can see it oscillates between -1 and 0. Okay, so what is the Mandelbrot set again? Well, to find the Mandelbrot set, we're interested in the values of c, which mean that the result stays small. And if we represent this graphically, we can find the Mandelbrot set. So we know it's going to all happen within a circle of radius 2, as soon as it's any larger than 2, it's guaranteed to blow up. And we tried two numbers, -1 and 1, and if you remember, -1 stayed small, but 1 didn't. So we know that not all of the points within this area are going to stay small. And if we keep on trying lots and lots of numbers, we get this black area, which is the Mandelbrot set. To recap, it is the set of the complex numbers c for which that function does not get large and instead remains bounded within 2. So why does it look like that? That's probably what Ben-oyt Mandelbrot was asking himself when he saw this weird, blobby, fuzzy picture in 1978. Today we've got these fantastic, ultra-clear pictures generated with computer programs which can show us the true nature of the shape. The reason it looks so fuzzy on the edges is because it's a fractal, sort of, because it's not perfectly self-similar. In fact, there are many slightly distorted copies of the Mandelbrot set within it, but generally it's regarded as a fractal. There's a lack of a mathematical answer really. It's just reality which causes it to look like this, which can bring up some, religious questions associated with why would something like this exist if there's no intelligent creator to oversee it, but I'll leave that out of today's presentation. So this is a 20-second long clip of us starting to zoom in to the Mandelbrot set, and we happen to be zooming into Seahorse Valley, as it's sometimes called, because some people thought it looked like that, but really you could keep zooming into this shape forever, anywhere along its edges, which is quite incredible. And I'm going to do a tactical fade to black. So what's the significance of this thing? Well, one thing is its surprising link to the bifurcation diagram, which has the logistic map of xn plus 1 equals r times xn multiplied by, in brackets, 1 minus xn. This thing is quite related to chaos theory, specifically to dynamic systems such as the population of mice. And the bifurcation diagram is another fractal, which I've got a video of, which you could zoom into forever. So for the example of a population of mice, xn is the population, xn plus 1 is the population next year, r is the growth factor, and the last bracket, 1 minus xn, is the environmental constraints. So for example, if the population is really high, then it's probably not going to grow much next year because of, possible starvation due to lack of food. And you can see in the top right hand corner the strange kind of way that the Mandelbrot set lines up to this diagram. And in case you're not entirely convinced by that, the next slide's got this nifty animation. So in this animation, the Zn iterates are plotted on the vertical axis, and the Mandelbrot set can display bifurcation. Aside from this, it's got these other interesting properties related to the Fibonacci sequence. So in this colored diagram, you can see that each bulb, which is each circular area, is numbered depending on the number of tendrils which it has. They're quite hard to see, but essentially on the edge of each circle, it's got these lines which will split up, and for 3, for example, it'll split into 1, 2, 3 directions. Now if we go from 1 to 2 and 2 to 3, and then look for the next lowest number in between, we get 5, and if we continue this, we get 8 and 13, and the Fibonacci sequence seems to emerge, and we can keep going down this route for as far as you can go, really. So thank you very much for listening. I've got a short summary on this slide if you've forgotten anything important, and yeah, that's about it.